Hello everyone, I'm Xavier, and you're probably tired of hearing this, but I'm also from the Safari Research Group at ETH, and today, together, we're going to talk about this thing called weightless neural networks and how to accelerate it using processing memory. I will first put the timer, which I should have done first. And here we go. So I will start with a high-level overview, with the problem motivation first. So I'm saying that deep neural networks are not suitable for mobile inference and training, especially training, because of high flop counts and large memory footprint. But weightless neural networks emerge as a viable alternative. They learn nonlinear activations via lookup tables. However, mobile inference and training of those weightless neural networks also remain a challenge because of random memory accesses with low reuse and high strides. However, computer systems with processing memory capabilities can alleviate this data movement related cost by placing computation near the data. Our contribution is that we simply implement weightless neural network inference and end-to-end training of weightless neural networks on a real-world processing memory architecture. We propose a model distribution scheme that results in an efficient use of this processing memory architecture. And we find an algorithmic improvements that boost the accuracy and allows for further model partitioning. Our results is that our implementation outperforms the CPU baseline by an average of 3.6x in inference and 2.9x for training with less than 256 DPUs. And we improve model accuracy by an average of 1 percentage point. So let's talk about mobile inference and training a little bit. Edge inference is a really crowded space. A lot of devices that have DRAM also have neural network accelerators, GPU, and powerful CPUs. However, on-device training is hard. Edge devices are power constrained, and TinyML focuses on quantization pruning, which makes the models not trainable. You cannot backprop anymore, so you cannot learn on the edge. However, on-device training is very valuable to fine-tune to user behavior and to adapt to system usage patterns. And so I posit that on-device training is the new frontier. So let's talk about this thing called weightless neural network. Probably no one here knows what this is, or maybe you do, because you guys know a lot of stuff. But this is basically what it does, and I don't expect you to understand every little stage of this, but it has a lot of stage. And for those of you who are familiar with Bloom filters, these are basically counting Bloom filters you can think about. And basically they learn nonlinear activations via lookup tables, this architecture. And I heard a lot of people asking me this great question, that how do these models actually learn? And I'm glad you guys brought this up, because I don't know either. And so if you guys know, please let me know after this. So the motivation for weightless neural inference and training, what are the challenges there? So again, you have this little weightless neural network. And let's talk about the bottlenecks. On both of these stages here, you have random memory accesses and random memory accesses with large strides and no immediate reuse. This is very bad. Also, you have parameters with no immediate reuse, but they are reused among the requests. So that, for example, if they go out of cache between requests out of LLC, this is going to basically cause expensive accesses to DRAM every request. And actually, there are parameters at each stage of this pipeline. Now, you're also probably very tired of hearing this, but we're going to use the UpMem processing memory architecture, and I'm really glad I'm last, so I don't have to explain all from scratch, because all the wonderful people here have already done a really great job. But this is basically the architecture. It's a bank, and you put a processor next to it. And I'll tell you exactly what you need to know about this architecture for my work. It has a 32-bit integer arithmetic, 8-bit multiplication only, so it's pretty weak cores. And the bank is 64 megabytes, and there's a scratch pad in between. That's going to be very relevant. You'll see why. And in this work, we're going to use less than 256 DPUs to represent an edge system. So there's one thing I didn't tell you about weightless neural networks that is very cool, is that I didn't talk to you about the friendliness of this architecture for the UpMem system. So every stage has logarithmic intensity and a lot of very simple operations. So memory operations, comparison, bit logic, and simple integer arithmetic. So these models learn with all these operations. They don't need all the very complex floating points that the UpMem processing memory system doesn't have. So now we finally get into the actual implementation. I've talked to you in the high-level overview of partitioning, and so you're going to tell me like, okay, why do you partition? Just do everything in one DPU. Why do you partition? Why do you care about this? And so basically, this is nothing new. You've seen this. This is from previous slide. On top, this is the weightless neural network. This is the processing memory architecture. And you see at those two stages, you have those random memory accesses. But what happens on the UPMEM processing memory system? Well, if you put the model in MRAM, which is a BEC, then because of how the DMA engine works and because of how our model architecture works, you're basically going to end up fetching a lot of bits that you're never going to use. So this is just as bad as CPUs. So what are we doing here? Well, we have a solution here. And so the solution is basically take those model parameters and you distribute it across many, many DPUs such that all the model parameters across the board all fit into the scrap-flat memory, this WRAM. And so this is basically what we get in the end. It's very exciting. Look, if you put everything into WRAM, all the random memory accesses are executed at a throughput of 1 per cycle. So this is amazing, I think. And I didn't tell you the best part, which is we actually have an algorithmic improvement that made all this possible, actually. So this is the standard way to shuffle the input in weightless neural networks. And we actually find that we couldn't really split the model if we use this kind of shuffling. But we found that actually, if we do shuffling block-wise, then not only does it enable the model partitioning that I was talking about, but it also improves the model accuracy. Very exciting. And so these are my results. For the algorithmic improvements, we do reordering by 1D block, and we find some good results across our datasets that we use. These are standard datasets in the weightless neural network research community. But we also find that reordering by 2D blocks gives even better results, as you can see here. And here are our performance results. So for inference, with 240 DPUs, we have an improvement of about 3.6x, and for training, 2.9x. And so now this is probably where you expect me to talk about future work. Unfortunately, I have this image instead, so this is probably you, and this is probably me. But in conclusion, I think weightless neural networks and processing memory are cool. I think research is awesome. And send me a hate mail to this address. Thank you, everyone.
We've got time for one question for Xavier.
Awesome.
Thank you.
I didn't get why these techniques, these optimizations are specific to the WRAM and TPU architecture. Can't you just play these same games on a conventional CPU? Yes, you can, but the benefits are not as great.
That's a really good point, and I'm glad you bring this up because you actually have a lot more aggregated WRAM. And also, there is a very interesting thing here, is that you have possible heterogeneity in your weights. So in the future work that I should have done here is that instead of having the same model split across many DPUs, maybe you can have a more, let's say, assembling approach. Does that answer your question at all?
So basically you take advantage of the much higher memory amount overall and amount of SRAM.
Yes.
But those things could be, I mean, maybe some kind of ablation study where you look at what those benefits would be in terms of accuracy, for example, on regular architectures would be interesting as well.
Yes, so we can implement the same reordering that we did for regular architectures, and they indeed improve accuracy even on CPU. It's architecture, doesn't depend on the architecture.
All right, let's thank Xavier.
Thank you.
And that concludes the